Happy learning. So in today's session we are going to discuss about Verilog HDL, and using Verilog HDL how can we describe the functionality of adder circuit, especially half adder and the full adder circuit. Now basically Verilog HDL. HDL is hardware description language. Hardware description language. Right. So this HDL, actually popular HDLs are Verilog HDL, VHDL and system Verilog is also one of the HDL, right? So the Verilog HDL is a very popular, most industry standard HDL. Most of the industry are using HDL, Verilog HDL nowadays. So which can be used to describe the hardware circuit, right? So for chip design, the Verilog HDL is commonly used language in all industry almost, right? So this general format or general syntax of this Verilog HDL program, right? So the program which can be used to describe the hardware circuit in Verilog can be called as a module. It's a basic building block for describing the logical circuit, right? Module is the keyword used in the Verilog. Basically, Verilog have been derived from the C programming language. Most of the syntax, whatever the syntax used to represent the keyword, identifiers and the statements, every syntax are also incorporated in Verilog HDL. This Verilog HDL has been standardized by the IEEE association, right? So now we can see the general format of the Verilog HDL. So first we have module declaration or module definition. There are 4 parts in the module of the HDL, Verilog HDL. So first one is the module declaration or module definition, we can say. This module declaration consists of the name of the module, the keyword module and the input and output port list. Input and output signals can be listed in this first part of the module program, Verilog program. This is basically as a block diagram, okay, block diagram of the digital circuit. Block diagram of the digital circuit is described as a module declaration. And then declaration part of the signals used in the circuit. Then statement part. The statement part, it gives the functionality of the circuit. It describes the functionality of the circuit. The functionality of the circuit is described in the statement part. And finally, termination part. Termination part, which can be implemented using the keyword end module. Okay, the entire program starts with the keyword module and it is terminated by the keyword end module in the Verilog HDL. Okay, so this is how we can categorize the part of the module of the Verilog HDL. So the first part, declaration, which gives the name of the design unit. For example, if you are going to describe the functionality of half adder, we can give the half adder as the module name. Before that, we have to give the keyword module. And whatever the signals, input and output signal we are going to use in the description of the half adder circuit, those signals can be listed in this module declaration. So simply the block diagram of half adder can be described as a module declaration in the program. Then the input and output signal can be declared with the keyword input and output, right? So we have to use the keyword here, input, output as well as in out, right? So what is the input keyword? It gives the details of the signal which receive the information from the external world, and the output, this is the signal which generate the information from the design unit to the external world, right? That in out is the bidirectional signal which is capable of receiving the input information from the external world as well as capable of generating the output information that can be transferred to the external world, right? So input and output keyword can be used for unidirectional signal, and that in out keyword can be used for declaring the bidirectional signal. Okay, the statement part, here only we have to describe the functionality of the hardware circuit. So that can be described in three mechanisms, right? So based on that mechanism used to describe the logic function of the hardware circuit, we can classify the modeling of the HDL program into three categories. So one is the data flow modeling, okay, data flow modeling. The another one is structural modeling, and behavioral modeling. Okay, so how this data flow modeling, structural modeling, behavioral modeling can be related with the functionality of the digital circuit. So when I say the digital circuit, the functionality can be described in three methods, right? So we can use the Boolean expression for describing the functionality, right? The Boolean expression, the functionality, the behavior of the logical circuit can be described in terms of mathematical modeling. That is the Boolean algebra we have to use, right? That Boolean laws and theorems we can use. By using that, we can derive the Boolean function, right? So that is the function. We can have sum of product function or product of sum function, right? So those are called Boolean functions. So if you directly implement those Boolean functions, right? So where the data input is manipulated at the input terminal, right? We can receive the input data from the input terminal that can be manipulated by using the logical function like AND, OR, XOR and XOR OR, by using all the basic logical function, and then the resultant output will be generated that can be assigned to the target variable, right? So here the data is obtained from the external world and it is getting manipulated and then it is transferred to the output terminal. So this is how the data is flowing from the input terminal to the output terminal. That's why it's called data flow modeling. So here we can implement this by using the Boolean expression, right? The Boolean expression can be simply implemented in the data flow modeling, right? This is one way of describing the functionality of the digital circuit. The another way of the digital circuit, so this Boolean expression which can be expressed as a sum of product function or product of sum function. The sum of product function can be implemented by using AND OR network, and this POS, product of sum function, can be implemented OR AND network. Okay, so this combination of and OR logic gates or OR and AND logic gates can be constructed as a logic diagram. Okay, the Boolean function can be implemented as a logic diagram, right? So that logic diagram gives the structure of the logic function. Okay, so the logic diagram which gives the structure of the digital circuit. So if we implement this logic diagram by invoking all the basic logic gates from the library of the Verilog, right? So that can be implemented as a structural modeling. The last one is the behavioral modeling, right? For each possible input condition, how the logic circuit is going to behave, how the output can be generated for all possible input condition, how it can be verified by using the truth table. Okay, the truth table is another mechanism for describing the functionality of the logic circuit for each and every possible input vector, right? So that is the behavioral modeling can be described by using for implementing this truth table. So this is how we can relate the functionality of the logical circuit for three mechanisms. What we have: the Boolean expression, logic diagram, truth table, that can be directly related to the corresponding modeling of the Verilog HDL. Okay, then what is the specific statement we are going to use for data flow modeling, structural modeling and behavioral modeling? In the data flow modeling, we have to implement the Boolean expression, no? So for that, we have to use the continuous assignment statement. Just we have to use the keyword assign and the assignment statement, right? So continuous assignment statement is the mechanism for implementing data flow modeling. And the structural modeling, so all the basic logic gates we have to use to implement this logic diagram. So we have the logical function for each and every basic logical operation, like for AND operation, for OR operation. From the name itself, for AND operation means AND, from the name AND itself there is one logical function, inbuilt function in the library. So we have to invoke those inbuilt function by using the instantiation statement. Right? By using this instantiation statement, we can implement the structural modeling. This structural modeling is further divided into three levels. So one is called the gate level modeling. Then another one is called switch level modeling. The third one is called the module level modeling. Okay, the structure itself can be further divided into three levels. So gate level, switch level and module level. Switch level means the functionality of the digital circuit can be described in transistor level, right? Very abstract, lowest abstract level is the switch level. So we can use NMOS, PMOS transistors, right? So CMOS transistor symbol. So for that the inbuilt functions are available. We can make use of those inbuilt functions and describe the switch level modeling. And the gate level modeling, so we have the logic diagram by using all the gate symbols like AND gate, OR gate, NAND gate, XOR gate. So for all those gates, they are inbuilt logical functions. We can write. So those logical functions can be invoked by using this instantiation statement. Gate instantiation statement we have to use for gate level modeling. Switch instantiation statement we have to use for switch level modeling. And then module level modeling. What is that module level modeling? Suppose I am going to design the full adder circuit. That full adder circuit can be designed by using two half adders. So first I have to write the code for half adder. That half adder code which can be used as a sub module in the main module of the full adder circuit. So in that way the larger logical circuit can be implemented by using the smaller modules, right? So that smaller module can be invoked in the construction of the larger module. So that's why it's called the module level modeling. Okay, so the module level modeling can be implemented by using module instantiation statement. Switch level modeling can be implemented by using switch instantiation statement, and gate level modeling can be implemented using gate instantiation statement. So in that way, the statement part can be used for implementing all the three modeling. So what is the statement used for implementing behavioral modeling? So here we have to use the mechanism which is called always statement. Always statement, or we can call it as a always block, right? So always statement and the initial statement also we can use for implementing the behavioral modeling, right? So always statement and initial statement. What's the difference between these two statements which are used to implement this behavioral modeling, right? The initial statement can be executed only once. It can be executed only once, but the always statement can be executed repeatedly. right? It can be executed repeatedly based on the conditions described in the behavioral modeling, right? So this is how we can understand how the program structure of the Verilog HDL will be available. After implementing the statement part, finally the entire program should be terminated by using the keyword end module. So this is how the entire Verilog module can have 4 parts. First one is the module declaration, second one is called declaration part, and the third one is the statement part, and fourth one is the termination part, right? So now by having this idea, we can start writing the HDL code for simply describing the functionality of the half adder circuit. So for describing this half adder circuit, so we should understand the basic concept. First we can start drawing the truth table for the half adder functionality and derive the Boolean function and draw the logic circuit. And for each and every part of this functionality of the half adder circuit can be implemented as a Verilog program. Okay, Verilog code. Right. First, take this half adder. What is half adder actually? This half adder is basically the combinational logic circuit which perform single bit addition. So we can draw the block diagram for that, right? So this is my half adder circuit. This half adder perform the addition. So it should perform addition using operands. So how many operand we have to use? 2 operand we have to use. Take it as A and B. So it can perform A plus B. So I am going to take the input variable A, input variable B. So both input variables should be a single bit variable. So it can generate the output. The addition resultant output of this addition is sum and carry. Okay, so this is the general block diagram of half adder. This block diagram only I am going to represent as a module definition or module declaration in the Verilog structure, Verilog program. Okay, then next one is, this is my block diagram of the half adder circuit, which I am going to mention as a module definition, or it can be called as a module declaration. Okay. Now the second step I have to follow, I should describe the functionality of this half adder circuit by deriving the truth table. What is truth table actually? The truth table is the table which gives the relationship between the input signal and the output signal. So this are my input signal of my half adder circuit. This is my output signal of my half adder circuit. Okay, so what is the relationship between the input and output? That relationship gives the functionality of the logical circuit, right? So I am having the truth table should have the input section and the output section. Okay, what are the input section? The input section should consist of my variable input A and B, and output section should have sum and carry. Okay, so because I have 2 input variable, the possible binary pattern that can be generated, right? The formula is 2 power n. So n is the number of input variable, means 2 power n binary pattern can be generated as an input pattern, right? So 0 0 is the first pattern. A and B both can have the value of 0. Then A can be 0, B can be 1, or A can be 1, B can be 0, or both A and B can be 1 1. So these are the possible binary patterns of the variables A and B. So for all these binary patterns, how the circuit going to generate the output? Basically going to perform the logical arithmetic addition, A plus B. Okay, so I have to add 0 plus 0. What can be my sum value? 0. What can be carry value? 0. 0 plus 1. So the 0 plus 1 will result sum as 0 No, carry is 0, sum is 1. Then 1 plus 0, A is 1, B is 0. When we perform A plus B, 1 plus 0 will result, sum value is 1, carry value will be 0. When I perform 1 plus 1, right, 1 plus 1 will give 1, 0. That is 0 is sum and 1 is the carry. Okay, so sum is 0, carry is 1. So this is how the truth table for the half adder circuit will be derived. So from this truth table, what we can understand for each and every possible input condition, how the circuit behaves, how the circuit generates the sum output and the carry output. So here the half adder is actually what operation is performing? Addition without carry. So previously if any operation is performed and the carry, if you want to incorporate, here we cannot incorporate. It can take only the operand value, right? So operand A or the operand B will be considered and the operation addition will be performed. So this is how the truth table for half adder. From this, how can we derive the Boolean function, right? So now the third step is the output function. What is the expression for the output variable? So the output functions can be derived, right? Take the sum output, take for which input condition the sum value is 1, it is the 0, 1 and 1, 0. Take only those conditions. For all this binary pattern, we can derive the variable format of the input pattern. So here A is 0, B is 0. It can be represented as A bar, B bar input condition in variable format, right? So A is 0 here, B is 1. So it can be A bar, B, and this is A is 1 here. So you can take A is in normal form, B is having the value of 0, take B in the complement form. So you can have A, B bar. And when I take A is 1, B is 1, both are appearing in the normal form or true form. So you have to write the for variable format as AB. These are called minterms actually. These are called minterms of the two variable function. So A bar, B bar, A bar, B, A, B bar, A, B. So for which minterm the sum output is 1. If you consider A bar, B and then A, B bar. So you can take my sum function which is equal to the combination of A bar, B plus A, B bar. Okay, which is expressed as A exclusive or B. This is the output function for my half adder circuit, sum output function. The same way, if we take the carry output is 1 only for one input condition which is 1, 1. That is A is 1, B is 1. So we can take the minterm which is AB. Okay, so directly we can express my carry is equal to the product of A and B, which is from the truth table we can derive. So this is how we can derive the Boolean expression for sum and carry output of the half adder. So for that, the last step is what? For deriving the logic diagram. Okay, logic diagram. So how can we draw the logic diagram, right? So we need to implement a sum function by using XOR operation. We need to implement the carry function using dot operator, which is the AND operator, right? So for this XOR operation, we have the logical gate, and for this AND operation, we have the logical gate. So we have to use one XOR gate, 2 input XOR gate, and one 2 input AND gate, right? So we can take the logic circuit using XOR symbol, XOR gate symbol. Okay, this is my XOR gate. Take A and B are the input and generate the sum output, which is equal to A XOR B. Okay, then take the input A and B, apply the input signal to the another gate which is called the AND gate, right? That AND gate output is my carry because it's going to generate A dot B. Now this is called my half adder circuit, right? So what is the circuit? Initially, we don't know what is the internal logic of this half adder circuit. While describing the problem statement, if you take the half adder, it should perform just a single bit addition. for performing addition we need two variable. So two variable and the resultant of the operation is sum and carry. Result of the operation sum and carry. So this is the block diagram only we have implemented here. What is the architecture inside the block diagram? Internal logic diagram, what is that? That we don't know initially. That is the thing derived by using this truth table and the Boolean function. From the Boolean function it has been implemented as a logic diagram. Okay, right? So now we can easily write the Verilog HDL code by incorporating all this information, right? First we can use this Boolean expression for implementing data flow modeling, right? And here we have to use the continuous assignment statement. Now we can use the simple assignment statement inside the always block for describing the behavior of the half-adder circuit using this truth table, and the logic diagram which is directly implemented by incorporating the logical XOR function and logical AND function. This is how we can write the Verilog HDL code very easily, right? So now we can start writing that code. Okay, for writing that we can categorize the style or modeling of the HDL code as a three types. First, the data flow modeling. Okay, the second one, structural modeling, or we can take the behavioral modeling here. Then we can take structural modeling, especially in structural we can take the gate level modeling. There are three types of structural modeling. In that we can take gate level modeling. Okay. First we can consider this data flow modeling. So look at this block diagram. A, B, sum and carry we have taken, right? This is the half-adder circuit. So this block diagram is going to be available as a module definition in all the three modeling. So first I am going to take module, the keyword, and then I can use half, or we can use just HA is the module name, half-adder underscore data, because it's the data flow modeling, right? This is the module keyword, module name. After that we have to list the signals of the half-adder circuit, input and output signal. Those are called IO port signal, right? So I can list A, B, sum, carry. Okay. Carry semicolon, right? This statement is called, the first statement is the module definition. Okay, this is common to all the three modeling, right? How the three modeling have been differentiated only in the statement part. Okay, so the same statement here in behavioral modeling I can write like module HA underscore behave I am going to give, BH I am going to give, because it's a behavioral modeling. Just I want to differentiate the modeling, for that one purpose only I am giving the different name here, and the IO port signal as it is A, B, sum, carry I can give. Okay, here also module the keyword and half-adder underscore structure gate level modeling. So I am going to give GAT, gate, half-adder underscore gate. Within the bracket I can give the list of signal A, B, sum, carry, semicolon. Okay, this is the module definition. The second part is what? Declaration part. whatever the signal I am listed here, I have listed here, all those signals should be declared either they are input or output signal. So I have to use the keyword input. I can use A comma B semicolon. Then the keyword output, the output signals are sum comma carry. Verilog HDL is case sensitive, right? So if you are going to use the small letters, we have to use small letters. Separate, there is a difference between the small letters and the capital letters. So it's a case sensitive, so we have to use properly in the software tool. Okay, then the same way here we can declare. So input A comma B semicolon, outputs are sum comma carry semicolon. In the behavioral modeling, so one thing we have to do it, while declaring the output signal, whatever the signal is declared as output, those signals should be declared with the data type register, right, in the behavioral modeling. So for that we have to use the keyword REG for register data type. That means there are two data types in the Verilog HDL, net data type and register data type. Net data type is nothing but a wire which connect the physical component, right? Simple physical connection represented by the net data type, and the register data type, it indicates that signals having storage capability, right? So in the behavioral modeling, we have to declare the output signal with the register data type. So we have to use the keyword reg sum comma carry. This is very important while describing the functionality using behavioral modeling. And in the structural modeling, we have to use all the input signal as a input keyword A comma B semicolon, output sum comma carry semicolon. So that's the declaration part is over, right? The next part is the statement part. By using the statement part only, we can differentiate all these three modules. So in the data flow modeling, we are going to use Boolean expression implementation just by invoking the continuous assignment statement. So for that, we have to use the Boolean expression. Sum can be expressed as A XOR B and carry can be expressed as AB. Okay, so for this, we have to use the keyword assign and then the assignment statement sum, which is equal to A XOR B semicolon. This is the operator XOR. Cap symbol is the operator which indicates the XOR operation. And then carry we have, so use assign, another keyword for implementing carry statement. So carry is equal to A ampersand B. This ampersand symbol indicate the logical AND operation. Okay. So these are the two statements to implement the sum and carry output of the half adder. Finally, we can terminate the program with the keyword end module. That's all about the half adder program in the data flow modeling. The same thing we can do in the behavioral modeling. Yes, in behavioral modeling, we can use one statement or block which is called always block, right? So use the keyword always at the rate of, this is the event symbol at the rate of, within the bracket, we have to list out all the input signal. Based on the input signal only, the output value can be modified, right? So you have to use the A or B. These are the input signal declared A or B. And then we have to use the keyword begin. Within the begin and the end keyword, we have to list the statement, simple assignment statement. So here we are using the procedural statement, here simple assignment statement. So the same syntax we are providing here except the keyword assign, right? So we can use sum is equal to A cap B and carry is equal to A ampersand B. So these are the simple assignment statement without using the keyword assign, right? So this simple assignment statement can be incorporated within this begin and end keyword in the always statement, right? So this is the syntax for always block, right? Always the keyword at the rate of, within the bracket we have to list the input signal. These input signals are called sensitivity list. The signals are called sensitivity list. They are called sensitivity list. What is the meaning of the sensitivity list? These outputs are sensitive to the values of A and B. Whenever some new event are occurred on A or B, at the time the sum and carry output will get updated, right? For example, my A, B are 0, 0. What my sum value? Sum will become 0, carry will become 0. Suppose I am going to set the A value as 1. What will happen? My sum value will be 1. Carry value will be 0. So like that, each and every possible value of A and B, my sum and carry value will be getting updated. Okay. So this is how the always statement will be executed repeatedly until some new event is occurred on the input variable A or B. Okay. So right, then we have to terminate the entire program with the keyword end module. So this is called behavioral modeling for half order circuit, right? Then the logical gate level modeling, right? The module definition is over, input part is over. Then the statement part is nothing but we have to use the gate instantiation statement. So what are the gate function we are going to use here? XOR function and the AND function. So for that we have the name XOR function. XOR, the name of the gate itself, there is a function. So XOR, within the bracket we have to list the output and the input signal. So in the syntax, in the gate instantiation statement, so first we have to list the output signal. So XOR gate can be used to generate the sum output, okay, by using the input signal A comma B. So this is the syntax. So before that, here one instance name we can provide. Suppose XOR gate is going to be invoked or instantiated more than once, more than one time, means we can differentiate that the occurrence of XOR gate by providing instance name. So here we are providing only one XOR gate, so no need to provide the instance name here, right? So the instance name is optional only, okay? So the XOR, the gate function name, within the bracket sum. First output must be mentioned and then the input signal can be listed. So by using the A and B, the XOR gate will generate the sum output. The same way, for implementing the carry function, we have to use the AND gate. Within the bracket, list the signal by mentioning output signal first and then the input signal. Then these two are called gate instantiation statement, and then the entire program should be terminated by using the keyword end module. Okay, so this is how we can write the Verilog HDL code for describing the functionality of the hardware circuit half order. Okay, so this is the simple understanding of the writing Verilog HDL. So we can develop, based on this we can develop the writing the code for all the other logical circuit. In the upcoming videos we can describe all the modules, right? Thank you for watching this video. God bless you.